A two-diode amplifier circuit is shown here implemented using one ideal op-amp and two diodes. Let's name them Diode D1 and D2. We want to see how this circuit is working and what is the Vout as shown here. And especially we want to draw the Vout as a function of Vin. So let's start with diodes. Assume that the diodes are off. So let's make the assumption that this diode D1 is off, this diode is off, and let's see how the circuit worked then. So in that case, what we have, if D1 off and D2 off. If that is the case, as if these diodes, they don't exist, that's the meaning of off. And as a result, the circuit is only simply a nice, simple inverting amplifier in the form of you have Vn plus minus Vn, and it goes to just a 40K, it goes to a 20K resistor, so 20K, and then it goes to the 40K resistor here, the feedback resistor. Then we have connection to negative input terminal of the op-amp, and positive terminal is grounded as shown in the circuit. And then it goes to the output voltage Vout. That's it. From output voltage Vout, of course, we have a 2K and then series with 6K this way. So series with 6K that is connected to negative 12 volt. And of course, on positive side, we have 2K in series with 6K that is connected to plus 12 volt. And that's it. So of course, to analyze this circuit, we only care about this segment because that is exactly an inverting amplifier. So we are dealing with a simple inverting amplifier. And as is known in this case, is as simple as saying that the gain of this amplifier is just writing the KCL here, or Kirchhoff current law, which says this current should be equal to this current, obviously. And because of virtual short, we have 0 volt here. Virtual short enforces that this op-amp has the same voltage at negative and positive input terminal. So as a result, 0 volt appears here as virtual ground. So having 0, then plus minus, we get Vin minus 0 divided by 20K. That's this current should be equal to 0 minus Vout across this 40K. So 0 minus Vout divided by 40K. And we get to what is obvious for the inverting amplifier, that says basically Vout over Vin, or basically we are just saying that Vout is negative 2 Vin. So when the two diodes are off in this scenario, then the relationship between input and output is a simple relationship that is Vout is negative 2 Vin. What is the implication of that? Implication of that is, if I show, say, an x-axis, let's say, just this way. So imagine I draw the circuit like this, the voltage transfer characteristic. So imagine this is input voltage Vn, and then we have the output voltage Vout. All right, so let's say, just for the sake of drawing things, let's say, so these are points on the X and Y, input output. Okay, so what happens is we have a Vout equal to negative 2 Vin. If I'm supposed to draw here, so when Vin is, say, 1 volt, Vout is negative 2. So this is 1 point. If Vin is 2 volt, Vout is negative 4. So this is another point. So if I just draw a line here, so this is the line that I have. Let's just shift it so that it's seen in a better way. Okay, so this is the line that I have. There you go. Now, These are the points, of course. Now, so this is the scenario when diode is off. But the question is, when is the case that one of these diodes will turn on? So for example, let's focus on diode D1 and imagine when it is that it's going to turn on. The moment that this diode wants to turn on is when the voltage at this point become roughly equal to 0, because this op-amp that we have in this circuit, assuming it's properly biased, so the supply voltages, whatever it is, let's say plus minus 12 volt, are connected, and as you can see, the negative feedback in this circuit is properly set up. So this op-amp, if it is biased, it has negative feedback, therefore it is stable, and it is assuming that it's not saturated in linear region. Virtual short is going to play, and virtual short, which I just used it, indicates that the voltage at positive input terminal is equal to the voltage at negative input terminal for op-amp. And since we have 0 volt here, as you can see, therefore the negative also would have a virtual ground at 0. So all I'm trying to say is the voltage here is 0 volt. So that is the voltage at the, in this case, at the left side of this diode. For this ideal diode to turn on, when it is off, the moment that on the right side of it, we get to 0, that's the moment the diode start turning on, and of course below 0, because this requires a voltage drop like this. In practice 0.7 volt, let's say, but in this case, ideal diode, it just need a barely positive voltage like with this polarity across that diode. So if this is the borderline moment when the diode start turning on, there is a current across the 6K, through the 6K flowing from 12 volt, and here is 0. So this current obviously is 12 volt divided by 6K or 6 kilo ohm, which means it's 2 milliamp. And then diode is still off, it's barely about to turn on, but while it's off, this current is flowing down, and when it is flowing through the 2K, that 2 milliamp times 2K will result in a voltage drop like this, which we can compute is effectively 4 volt, because it is 2 kilo ohm times 2 milliamp, which is 4 volt. Now, since at this node we have 0 volt, let me highlight it. So since we have 0 volt here, and we have plus minus 4 volt drop across this, at the moment that diode D1 is about to turn on, the voltage here is negative 4 volt. Alright, so what is the consequence of this? Well, take a look at our partial voltage transfer characteristic, or VTC, that we just draw. The moment that output gets to negative 4, which is here, volt, and input naturally is plus 2 volt because of the kind of relationship that we have seen existing between input-output during the time when two diodes are off, we are about to see a different behavior. Right at this point, the diode D1 turns on. So what happens is now diode D1 turns on. So let me go back to the color. So now we have D1 turns on and D2 is still off. So then what is the lookup circuit then? Okay, so in this situation, the lookup circuit is now in this way. So the circuit gonna look like we have Vn that is going through 20K to the op-amp. Okay, so op-amp is minus plus, and then we have the 40K. Of course, the feedback resistor is still there. Okay, what else do we have? The diode is now on. When the diode is on, it's an ideal diode, D1. So it will connect the input negative terminal of op-amp or inverting terminal to this point that I'm highlighting. Let me change the color so that it's obvious which points I'm talking about. This point will get shorted via diode to this point. So as a result, what's going to happen is this 2K resistor will be in parallel with the 40K resistor. So as long as D1 is on. So we get 2K. And then what happens is this node, which is here now, will be connected still to 6K to 12 volt. So what I'm going to have is we have 6K or 6 kilo ohm, and then we have the positive 12 volt. Okay, so, and of course here is V out, and on the other side of the circuit, diode D2 is off, so we still have the same setup as I showed here, meaning I have 2K, and then I have, let me show it this way, and then I have 6K kilo ohm connected to negative 12 volt. Alright, so the circuit is still an inverting amplifier because of the way the topology of circuit is, but now we have two voltage sources connected, and we can write as simple as just a KCL, again, the Kirchhoff current law of preservation of current at this point. So that makes it easy because virtual short is still valid for the op-amp, as you can see. So here we have 0 volt, we have then as a result same 0 volt or virtual ground on negative terminal. So here we have as a result 0 volt. And then we can therefore we can say the sum of this current and this current should be equal to this current plus this current. The incoming current should be equal to outgoing current from this node, and nothing can go through the input terminal of ideal op-amp because it has practically infinite impedance, so nothing goes there. Okay, so writing a KCL or Kirchhoff current law, I can say 12 minus 0 divided by 6K, that's the top current here, and then plus Vn minus 0 divided by 20K is equal to, now outgoing current, 0 volt minus V out. These are the voltages across 2K, so it will be 0 minus V out divided by 2K, and finally 0 minus V out, so it would be just simply 0 minus V out divided by 40K. Or effectively 2K and 4K are in parallel. So we can therefore get to this point. Let me go back to my original color. So it would get to this point that V out is just negative 2K parallel with 40K as feedback resistor times Vn divided by 20K plus 12 over 6K, which means this 12 over 6K, which means 2 milliamp. Okay, so as my last attempt here, I can just say as a result, when I simplify everything, you can see that 20K times parallel with 40K, this whole thing here becomes 2 times 40 divided by 2 plus 40, which is 42. And then we have divide by 20K here. So all I'm saying is on this side we will have 40 divided by 21, and then we end up with having V out equal to negative 2 over 21 times Vn, and we have, of course, negative 80 over 21. This is, of course, we need to be careful that the result of this whole process and calculation becomes, you're dealing with a kilo ohm here, so we need to be careful about what we are doing. So this is K. So that multiplied by 2 milliamp ends up to giving us just minus 80 over 21. So this is the linear, basically this is the equation or line that relates the input voltage Vin to output voltage Vout in the scenario that diode D1 is on, but diode D2 is off. So what is it saying? If we look at it and try to draw it, all right, so it means that the tangent or the slope is still negative, but it's much smaller, almost negative 0.1. So we used to have a tangent of negative 2, so much sharper drop. Now we have suddenly much considerably slower drop, something like this. I'm just showing it. So this tangent here is very small, the negative 0.1 that I talked about. So let me make sure that it's visible. So negative 0.1 tangent. All right, so that is this is the situation that I'm showing here. The last point that we need to talk about is when the diode D2 is on and D1 is off. So that would be, I'm gonna write it here. So I'm gonna write it right here. Okay, so what scenario I'm talking about? It is if, so the scenario that D1 is now off and D2 is now the one that turns on. So turns on. Okay, so what is this? How is this working? Okay, so let's focus on the circuit. So if D1 supposed to be off, but D2 is going to be on, so this one turns on. Let's consider that because of voltage here being 0 volt, so on the left side of this diode D2 we have 0 volt due to virtual short of op-amp 1. So if the diode D2 is off but is about to turn on, it means the voltage at the right side here is just about to get to 0. So if that is the case, you can see that, let me change the color so that it's visible on the, so from 0 to negative 12, there is a current that is going like this through the 6K resistor. So there is that current that going through the 6K resistor. Okay, so diode D2 is about to turn on, not yet turned on. At that moment, this whole current should come down from V out via 2K. So of course, this current that is going through this 6K is easy to compute. It's the current result in a voltage drop like this across 6K, which is just 0, negative 12, so 0 minus 12 divided by 6K. So the current is obviously 2 milliamp, this current. When that 2 milliamp is going through this 2K resistor, it causes a voltage drop like this that is equal to 2 milliamp times 2K, which is 4 volt. So if this is 0 here, at that moment, here is plus 4 volt. Okay, so we are here basically. So 1 volt, 2 volt, 3 volt, 4 volt. I'm drawing on the VTC, voltage transfer characteristic. So at 4 volt, Vin of the whole circuit is at negative 2. All I'm trying to say is we are talking about this moment. At that moment, when the circuit turns on, the look-off circuit is exactly now, I'm going to draw it here. So we have Vn plus minus, and we have ground. We have a connection via 20K kilo ohm resistor to the negative input terminal of the op-amp. Op-amp positive terminal is grounded. As you can see, if this diode D2 turns on, it will connect. It will result in having this 2K resistor appearing in parallel with 40K, because on one side they have common node and the other side will get connected when D2 turns on. So what I have is I have the usual 40K, but then I have a 2K in parallel with 40K, the 2K that comes from the bottom of the circuit. This goes to V out. Okay, and of course from Vout we have what else do we have? You can see that from this node, if I change the color back to something that we can see, so from this node that is now same as this node, we have a 6K that connects to -12. So we have 6K that connects to -12. Okay, so what is the meaning of that? I am talking about a 6K resistor that is connecting to -12 volt at the bottom of circuit. Okay, what about the top of the circuit? Basically, what about the stuff that we have on top? Well, that doesn't matter, because effectively it just means that you have 2K, because diode D1 is off, we have 2K in series with a 6K connected to +12 volt. Let me shift this whole thing a little bit so that you can see it more correlated to the scenario that I'm saying. If diode D1 is off, diode D2 is on. So this is the look of circuit. If this is the look of the circuit, then it's easy to just say that, okay, focus on the inverting amplifier that we have here, which means focus on this portion that matter to us. And same idea, write a KCL at this point. The virtual short requires that if we have 0 volt on positive terminal, we have 0 volt on negative terminal as well, virtual ground. So again, the same as before, KCL required that the sum of incoming currents through the 6K and 20K should be equal to the sum of the outgoing current. That is, those are the current going through the 40K and 2K. We can make the assumption that the 2K and 40K are in parallel with each other as feedback resistors. So if we write KCL, or Kirchhoff current law, law of preservation of current, it just simply becomes Vn divided by 20K. That's the current through the 20K, given that on one side of it we have 0 volt. And then we have -12 volt, the other supply, divided by 6K. So these are the incoming current. Equal to outgoing current. And outgoing current is just the current that is going through both the parallel of 2K and 40K with 0 and V out on the two sides of them. So I would say just 2K parallel with 40K. So in summary, in this case, what I have is V out is simply minus 2K parallel with 40K. All right. And then we have Vn divided by 20 minus 12 divided by 6K is 2 milliamp. So, and we have a negative, we have the negative negation at the very beginning. So if we further simplify this, what we get in this situation is V out is simply minus same tangent as before, same slope, minus 2 over 21 Vn. Okay, what else do we get? We get plus this time 80 divided by 21. So this is the line that is sort of a linear it's VTC for the input to output in this scenario. If I go back and try to draw this one, so if I try to draw this one, you will see that I'm talking about, okay, so let me see if I can draw this one. There you go. I'm talking about this line, and I am talking about same negative tangent that I showed you. So we are dealing with this negative 0.1. So negative 0.1, and that is this slope. So basically, in summary, we have a combination of, if I can highlight it, we have the combination of this slope, I mean this line, and this line here. So this is our voltage transfer characteristic, or VTC, for this circuit. The breaking points from perspective of input are these points. So are 2 volt at input Vin. At that point we have one breaking point here in which the characteristics start changing. Also at negative 2 volt at input, corresponding to 4 volt at the output. The other one is negative 4. We have also a change there. So this is the voltage transfer characteristic for this circuit. Okay, I hope that this example is helpful in terms of showing the process in which we can analyze a multi-diode amplifier circuit that has a piecewise linear VTC that depends on when the diodes turn on. The shape of VTC will change. So it is useful in terms of being able to design multimodal amplifier effectively. I hope that this example is helpful.